And I'm from the Buddhi Academy. So today we'll continue with the chapter that is the DNF block elements. In our last video, we have seen about the catalytic properties, formation of interstitial compounds, alloy formation, formation of colored ions, and even the magnetic properties of the transition metals. Now today we'll see some of the important compounds of the transition elements. Okay, there are some important compounds and their formations or preparations we'll see today. So first is the oxides and oxoanions. Okay, oxides and oxoanions. Now what are oxides? Oxides are generally formed by the reaction of metals with oxygen. So when metals react with oxygen, at that time an oxide is formed. For example, Cu2O. So this is a cupric oxide, copper oxide. Whereas I think was a famous experiment which was carried out when you were in 10th standard. That is the Mg plus O2. You get something known as MgO. It is magnesium oxide, right? So this was a famous experiment. You have burnt magnesium ribbon in presence of oxygen and you got magnesium oxide. So this is known as metal oxides, or when metals react with oxygen, they form something like this. These are known as metal oxides. Okay. Now, all the metals except scandium, okay, there is an exception. Scandium doesn't form a metal oxide, okay, with which are ionic. So scandium, they doesn't form any metal oxide which are ionic, even though it forms a metal oxide, but that is a stable one. It is not an ionic one. So the highest oxidation number in the oxides coincides with the group of number, and it is attained as, now scandium has an oxidation state of +3, so it is Sc2O3. Manganese has a oxidation state of +7. Highest oxidation state is +7, so it is Mn2O7. So beyond group 7, no higher oxides can be formed. Only a higher oxide of iron can be attained because iron has a oxidation state of 6. Okay. Besides oxides, they can be used to stabilize oxocations. Oxocations means here, vanadium is stabilized using O2, but it attained a plus sign. Okay, oxygen has attained a plus sign. So this is an oxocation. Okay, because oxygen is having a positive charge, but it is stabilizing the metal atom. Okay, that's why it is known as, besides oxides, the oxocations stabilizes the metal atoms. Now, as the oxidation number of the metal increases, ionic character decreases. So, as the oxidation number increases, okay, of a metal, the ionic character decreases. Okay, in case of Mn. Now, here MnO7, Mn2O7 is a covalent green oil. It is a stable molecule. Even in CrO3 or V2O5, they have a low melting point. This is because the oxidation number increases, which decreases the ionic character. Okay, in these higher oxides, the acidic character is predominant. Okay, predominant means they are considered to be acidic in nature. Now, thus Mn2O7 gives HMnO4 and CrO3 gives H2CrO4 and H2Cr2O7. So these are some kinds of molecules. Because of their higher oxidation state, these molecules give forms these compounds. Okay. However, amphoteric, though mainly acidic, and it gives V4 3 minus as well as VO2 plus salts. So these are the molecules which are formed by MnO2 and CrO3, whereas V2O5 is an amphoteric molecule. It is mainly acidic and gives VO4 3 minus as well as VO2 plus. So you amphoteric means you get a negative molecule also and you get a positive salt also. That's why it is an amphoteric molecule. Now in vanadium, there is a gradual change from the basic V2O3 to less basic V2O4 and to amphoteric V2O5. So V2O4 dissolves in acids to give VO2 plus salts. These are some examples how you can convert the metal oxides, or what are the molecules that can be formed by metal oxides. Basically, they can form salts. Okay, and there is an amphoteric characteristic. They can form both positive as well as negative salts. Now, first we will see the preparation of potassium dichromate. Potassium dichromate is K2Cr2O7. This is potassium dichromate. Now, potassium dichromate is a very important chemical used in leather industry. So it is a very important, potassium dichromate is a very important chemical and it is used in leather industry, okay, for the formation of leathers. Now, and as an oxidant, now it is potassium dichromate, it is used in leather industries and also as an oxidant. Okay, it is an oxidizing agent for preparation of many azo compounds. Now, dichromates are generally prepared from chromates. Okay, dichromate, it is prepared from chromate. Now, which in turn are obtained by the fusion of chromite or ore. Now, potassium dichromate, it is prepared from chromate, but chromate is prepared from chromite ore. Okay, chromite ore is FeCr2O4. This is chromite ore. From this chromite ore, we get chromate, and using this chromate, we can form K2Cr2O7. Okay. When you combine this chromate ore with sodium or potassium carbonate in free excess of air, okay, that time you get chromate. Okay, when chromite ore is combined with potassium or sodium carbonate, either with potassium or sodium carbonate, you get free access to air. Now, this reaction of sodium carbonate occurs as follows. Now, what is the reaction? So, here you can see it is the chromite ore. Okay, the chromite ore is mixing with sodium carbonate and oxygen. So, in presence of free air, they said. So, free air as an excess. So, they should have excess of free air. And air, as you know, contains oxygen. So, when you mix chromite ore with sodium chromate in presence of air, okay, you get sodium chromate, iron oxide or ferric oxide, and carbon dioxide is released out. Okay, so the reaction is FeCr2O4 plus Na2CO3 gives O2 plus O2 gives Na2Cr O4, that is sodium carbonate, sodium chromate. This is sodium chromate. This is ferric oxide plus that is released out. So the yellow solution of sodium chromate. Okay, sodium chromate has a color of yellow. So it is an yellow color solution. So the yellow solution of sodium carbonate or sodium chromate is filtered and acidified with sulfuric acid. Okay, so once you combine FeCr2O4 with Na2CO3 plus O2, you get something like Na2Cr O4 plus you get Fe2O3 and carbon dioxide is released out. Now this sodium chromate is yellow in color. Okay, this yellow color solution is later filtered out. Okay, and it is acidified using sulfuric acid. Okay, later to this Na2CrO4 we add sulfuric acid to give a solution from which orange sodium dichromate Na2C2O7 2H2O can be crystallized. Now, as I told you, potassium dichromate, okay, potassium dichromate we want to form. Now, to form potassium dichromate. Dichromate means you have to have two chromium in it. Now, in this reaction, you can see there is only one chromium. Okay, that's why we add sulfuric acid to acidify it, and by doing this, you get an orange color sodium dichromate solution. Now, this is just sodium chromate, which is yellow in color. So, when you add sulfuric acid to it, this becomes sodium dichromate. Sodium dichromate means it will become Na2Cr2O7. Okay, it will become Na2Cr2O7, which is orange in color. Okay, and from here we can prepare the potassium dichromate. So for preparing potassium dichromate, first what we have to do is we have to prepare a chromate from chromite ore. Okay, so here we have taken iron chromite ore. To this ore we have added sodium carbonate, and it was done with free access of air or in the open. So there is a passage of oxygen. In this we attained or we got sodium chromate, which is yellow in color. But we want dichromate, right? But we only got a chromate here. So to make it dichromate, what we did is we filtered the sodium chromate and acidified it using sulfuric acid. Okay. By acidifying it using sulfuric acid, we get a orange color solution, which is the sodium dichromate. Okay. Now, this sodium dichromate is more soluble than potassium dichromate. Okay, sodium dichromate is more soluble than potassium dichromate. So therefore the prepared by treating the solution of sodium dichromate with potassium chloride. Now, how you will convert the sodium dichromate to potassium dichromate? It is very simple. What you have to do is, to this sodium dichromate, that is Na2Cr2O7 is the sodium dichromate, which is more soluble than potassium dichromate. This is already prepared, a orange color solution we have. To this solution, we have to add KCl, that is potassium chloride. Now, what will happen here is, as you know, Cl and Na are more relatable, right? So what will happen is this potassium will replace sodium here. So this will become K2Cr2O7 plus Na will combine with Cl, giving you NaCl. What is NaCl? It is a salt. Okay, this is a salt which is readily soluble in water. Now, this is your potassium chromate or potassium dichromate. So now I hope you have understood how you prepare potassium dichromate. Now I'll explain it in simple way again. So for preparing potassium dichromate, that is K2Cr2O7, what we have to do is it is prepared from a chromate. Okay, prepared from chromate. Now from where this chromate is prepared? Chromate is prepared from chromite. Now preparation of K2Cr2O7, we have taken an iron chromate. Okay, FeCrO4. Okay, here you can see we have taken a iron chromate. Okay, iron chromite. Okay, FeCr2O4 plus to this chromite we have added sodium carbonate, Na2CO3. Now this reaction should have free access of air. So air should continuously pass through this reaction. Now what does air contains? Air contains oxygen. Okay, so there is also supply of oxygen. This gives NaCrO4 or Na2Cr O4. This is sodium chromate. Byproducts that are formed along with the main product. The byproducts are Fe2O3 and carbon dioxide gases released out. Okay. Now we got sodium chromate. Now with sodium chromate, what we have to do is, this is a chromate. What we are preparing is a dichromate. Okay, we want 2 chromium. Yes or no? So for getting the chromium doubled, what we have to do is take the sodium chromate, that is Na2CrO4. This is sodium chromate. We have to acidify it using sulfuric acid. Okay, using sulfuric acid, we have to acidify it. When we acidify it using sulfuric acid, what we get is Na2Cr2O7. This is a sodium dichromate. Now we got sodium dichromate. Now what is the last step that is remaining is, we have to replace this sodium from potassium. Yes or no? We want potassium dichromate. Now we got sodium dichromate. Now how we will separate sodium dichromate from, or make sodium dichromate, or convert sodium dichromate to potassium dichromate? For doing that, we have to just do a double displacement reaction, that is Na2Cr2O7. Now we have to replace this Na2 with potassium. So use a potassium chloride. Here what will happen? This potassium will replace the sodium. Okay, so it will become K2Cr2O7 plus. This sodium, it will combine with Cl. Okay, so it will become NaCl, which is a salt molecule. Now we got our product, that is potassium dichromate. So this is how we prepare potassium dichromate. Okay, so this is the preparation process of potassium dichromate. Orange crystals of potassium dichromate crystallizes out. So when you keep the solution for evaporation, you will get orange color ka crystals, which are your potassium dichromate crystals. Okay. Now the chromates and dichromates are interconvertible. So as you know, from chromate we form the dichromate. So from dichromate we can form chromate also. So they are interconvertible in aqueous solution. So whenever they are present in a aqueous solution, they are interconvertible, which depends on the pH of the solution. The oxidation state of chromium in chromate and dichromates is same. So the oxidation state will of chromium, okay, oxidation state of chromium will remain same in chromate as well as in dichromate also. This is an chromate ion and this is an dichromate ion. So you can see there are two chromium and this is only one chromium. Okay, so these are the structures of chromium and dichromium. Sodium and potassium dichromates are strong oxidizing agent. Whether it is sodium or potassium, both dichromates are strong oxidizing agents. Now, the sodium salt has a greater solubility in water and is extensively used as an oxidizing agent in organic chemistry. But sodium, you know, NaCl is a salt which is readily soluble in water. So, sodium being a salt and has a greater solubility in water, it is extensively used as an oxidizing agent, or it is more frequently used as an oxidizing agent in organic chemistry. The potassium dichromate is used as a primary standard in volumetric analysis. Now, potassium dichromate, I hope you all know about the purple color solution which we use for titrations. Okay, the burette solution, purple color burette solution which we use for uh, volumetric titrations. So we use it for the, we use it as a primary standard for volumetric analysis, that is potassium dichromate. Now in acidic solution, its oxidizing action can be represented as follows. So, oxidizing action, how it can be oxidized. Cr2O7 2 minus. Now 2 minus because we have removed two sodium or potassium molecules from here. That's why it is 2 minus. Plus 14H plus 6 electrons. Now, dichromium or dichromate plus hydrogen ions plus electrons. We will get chromium with plus 3 oxidation state and H2O. Okay, thus the acidified potassium dichromate will oxidize iodides to iodine. So here what will happen? This potassium dichromate, it can oxidize iodides to iodine, sulfides to sulfur. Okay, tin 2 to tin 4, iron 2 to iron 2 salts to iron 3. So it is Fe2 plus to Fe3 plus. Okay, this can be converted. So this is the oxidizing power of the potassium dichromate. So here you can see I told you iron 2 to iron 3. A reaction is given here. This is dichromate ion plus hydrogen ions, and this is Fe2 plus, as I told you, Fe2 to Fe3. So here you can see it is converted to Fe3 plus. Okay. Next is the potassium permanganate. Sorry, this is not a purple color solution. This is a orange color solution, and potassium permanganate is a purple color solution. So this is KMNO4. That is the potassium permanganate. Now, first is the potassium dichromate. Now we have potassium permanganate. Now, potassium permanganate is prepared by the fusion of MnO2 with an alkali metal hydroxide and an oxidizing agent like KNO3. Now, MnO2, okay, MnO2 is the ore. Okay, this is the ore. Since K2Cr2O7, that is potassium dichromate, is formed or prepared from chromite ore. For KMnO4, that is potassium permanganate, we use MnO2 ore, which is known as pyrolusite ore. Okay, MnO2 is known as pyrolusite. And oxidizing. Now, when you combine this MnO2 ore with an alkali metal hydroxide. Alkali metal hydroxide can be NaOH, KOH, okay, any metal hydroxide. It should be alkali. Alkali metal hydroxide and an oxidizing agent like KNO3. Okay, which is potassium nitrate. This produces the dark green K2MnO4. So by doing this, we get a dark green color ka solution which is K2MnO4. Okay, K2MnO4. Now, which disproportionates in a neutral or acidic solution to give permanganate. Now we don't want K2, we want only K. So by disproportionating it using a neutral or acidic solution, we get KMNO4. Now let's see the process in detail. So first what we have to do is we have to take the MnO2 ore. Okay. To that we have to add an alkali hydroxide, that is KOH. Here we have taken KOH. In presence of oxygen, we get K2MnO4. Now K2MnO4 is a dark green color ka solution. Now to K2MnO4, we have to use an acidic solution. By using an acidic solution, we get KMNO4 and MnO2 ore is again released, which will again we can use for the preparation of KMNO4 solution. Now, commercially, it is prepared by alkaline oxidative fusion of MnO2 followed by the electrolytic oxidation of manganate. Now, this is a laboratory method how we can prepare. But in industries of a commercial purpose, they require large amount of thing and should be quick enough, right? The formation of acid should be fast. Now, this what these commercial people do is they take MnO2, okay, fuse it with KOH and oxidize it with air or KNO3. Okay, this first process. Either you oxidize it with air or KNO3. KNO3 is the most common method used by the commercial people to fasten the process. You get a manganate ion. Now this manganate ion, using electrolytic oxidation in alkaline solution, you get permanganate. Okay, here we are acidifying it using a neutral or acidic solution. Here we use electrolytic oxidation. Okay, we use electricity to fasten the process. We use electrolytic oxidation in an alkaline solution, due to which manganate ion is converted to permanganate. Okay, now we have seen the preparation of K2Cr2O7. Next, what we prepared is KMNO4. This is a potassium permanganate. So for preparing potassium permanganate, what we have done is we have taken MnO2, which is the ore which is used for the preparation of KMNO. To this MnO2, we have added KOH, that is alkaline hydroxide, plus O2. In place of O2, we can also add KNO3. Okay. Now, this will give you K2MnO4, which is a green color solution. Okay, so this is a green color solution. Now, we got potassium manganate. Now, this is a manganate ion, or this is a manganate product. What we want is a permanganate, right? So, taking this manganate, that is K2MnO4, if I oxidize it, H plus ions, using H plus ions, if I oxidize this, okay, what I get is KMNO4, which is the potassium permanganate, and is in purple color. So this is how we prepare potassium permanganate. Okay. In laboratories, a manganate ion salt is oxidized by peroxide sulfate or permanganate. So in laboratories, a manganese ion salt, if you want to oxidize it, then it is oxidized using peroxide sulfate or peroxide sulfate to manganate, okay, or to permanganate. So here you will take Mn2 plus ion using H2O8, which is the peroxide sulfate, okay, and in presence of water you get permanganate. Now potassium permanganate forms dark purple color solution, almost black. If you take a little and see, it will be in a dark purple color. But if you fill a beaker with potassium permanganate solution, it is a dark purple and it almost looks black in color. A crystal will form if you evaporate the solution. A dark purple to almost black color का crystal will be obtained, which are isostructural with those KClO4. So KClO4 is another compound. These crystals of KMNO4 resemble similar to it. It is an isostructural with the KCl4 solution or crystals. The salt is not very soluble in water. Now this potassium permanganate, it is not very soluble in water. But when heated, it decomposes at 513. So if you add potassium permanganate into water and shake it or mix it using a glass rod, it is not soluble. But if you heat it, okay, if you heat it at 513 kelvins, it will decompose. Okay. Now, if you decompose KMNO4, okay, KMNO4 will form K2MnO4, MnO2 and oxygen. So whatever molecules you take for the preparation of KMNO4 will be given out. Okay. Now it has two physical properties of considerable interest. Now KMNO4 has two physical properties which are considered interesting. Now, first, let's see what it is. It's the intense color and its diamagnetism along with temperature dependent weak paramagnetism. Now, what are they? One is its intense color, the dark purple to almost black color, and next is its diamagnetism. So, KMNO4 are diamagnetic, but as you know, it depends upon temperature also, because when you heat KMNO4 at 513 Kelvin, it decomposes, right? So it is a temperature dependent one. Now, since it is temperature dependent, it also shows a weak paramagnetism. So a molecule which shows both diamagnetic and paramagnetic characters. That is also one of the considerable feature of KMnO4 molecule. The green manganate, now this can be explained by the use of molecular orbital theory, which is beyond the present scope. Now, why it is, we can explain it using MOT theory. Okay, MO theory, that is molecular orbital theory, which is not that important here. Now, the magnetic and the manganate and permanganate ions are tetrahedral, and pi bonding takes place by overlap of p orbitals of oxygen and d orbitals of manganese. Now here, both manganate and permanganate both have a similar tetrahedral structure. You can see both structures are same. Okay, only and the pi bond, the double bond is formed between the overlapping of p orbitals of oxygen. And this double bond or pi bond is formed because of the p orbital ka overlapping of oxygen with d orbitals of manganese. Okay, now the green manganate is paramagnetic because of one unpaired electron, but the permanganate is diamagnetic due to the absence of unpaired electrons. Now, manganate ion, this one is paramagnetic. Okay, this is paramagnetic because of its unpaired electrons. And diamagnet permanganate, okay, permanganate is diamagnetic. So this is diamagnetic. Why this is diamagnetic is because of the absence of unpaired electrons. Now, if you get a question why, what is why paramag why manganate is paramagnetic and permanganate is diamagnetic, is basically because of their unpaired electrons, presence and absence of unpaired electrons. Manganate has unpaired electrons, due to which it is paramagnetic, whereas permanganate has no unpaired electrons, hence it is diamagnetic. Now, acidified permanganate solution oxidizes oxalates to carbon dioxide. Okay, permanganate solution, it oxidizes oxalates to carbon dioxide solution. Now, this is an oxalate. Okay, COO minus, COO minus. So, this is an oxalate ion. So, permanganate solution, it converts these oxalate ions to carbon dioxide. Okay. Another one is conversion of iron 2 to iron 3, nitrides to nitrates, so NO2 to NO3, and iodides to free iodine. Okay. So it is basically an oxidizing agent. Now the full reaction can be written by adding the half reactions for KMnO4 to the half reactions of the reducing agent, balancing whenever necessary. Now, how you will write a full reaction for this? Full reaction you can write by using a half reaction method. So, half reaction for KMnO4 to the half reaction of the reducing agent. Now, if we represent the reduction of permanganate to manganate or manganese dioxide and manganese to salt by half reactions. Now, these are the half reactions where permanganate, okay, permanganate is converted to manganate, manganese dioxide, and manganese to salt. Here you can see permanganate with the loss of with gain of electron, it has turned to manganate. Okay, here again permanganate, oxidizing it using 3 electrons, you get a manganese oxide, manganese dioxide, which is the ore which is used for the preparation of permanganate. And when you again oxidize it using little higher oxidizing agent, you get an Mn2 plus salt. Okay, now we can very well see the hydrogen ion concentration of the solution plays an important part in the influence of reaction. As you can see here, the concentration of hydrogen ion, it plays an important role in the reaction. It influences the reaction. Now, although many reactions can be understood by considering the redox potential, kinetics of the reaction is also an important factor. Although we can understand this because of the redox potential, but here kinetics of the reaction is also important factor. Now, permanganate at H plus is equal to 1 should oxidize water, but in practice the reaction is extremely slow unless either Mn manganese 2 ions are present or the temperature is reached. Usually permanganate, when you have only one H plus present, it should oxidize the water. But when you practically do that experiment, the reaction is found to be very slow. Unless you heat it or you increase the temperature, the speed will increase, or you convert the manganese or permanganate to manganese ions. In these cases, the reaction will faster. Now, a few important oxidizing reactions of KMnO4 are given below. Now, these are the few important oxidizing reactions of KMnO4. Okay. Now, first in acid solutions. So, oxidizing in acid solution. Iron is liberated from potassium iodide. Now, here we have taken I minus means it is Ki. So, potassium iodide, and we have used permanganate in presence of H plus. You get manganese ions and iodine. Okay, I minus to I2. So, it has converted iodide to iodine. Fe2 plus to Fe3 plus. Again, using permanganate also you can convert Fe2 plus to Fe3 plus. Here also manganese ions are released. Now these are some more examples of oxidizing reactions of oxidizing reactions using permanganate. Titration in presence of hydrochloric acids are unsatisfactory since hydrochloric acid is oxidized to chlorine. So when you use permanganate for titrations in presence of hydrochloric acids, it is unsatisfactory because hydrochloric acid is oxidized to chlorine, not to hydrogen. Okay. So in today's class, we have seen about the preparations, or we have seen about oxides and oxoanions of metals. In this, we have also seen the preparation of potassium dichromate and potassium permanganate and few of their reactions. So in our next class, we'll start with the inner transition elements. Okay. So thank you for watching my video. Please do like, share and subscribe to our channel.